Okay, hello everyone. Welcome back to our seminar. And today's Hendrik van Maldeghem is going to talk about geometric approach to some ring 3 graphs.
Okay, thank you very much. I first want to start by thanking the organizers, of course, to invite me for this virtual seminar. I think that's one thing, one good thing that came out of this Corona business, that we have all these virtual seminars now, well, all these, at least some of them. I first want to get rid of that message here that the meeting is being recorded, but I don't see my cursor, so it's kind of hard to.
It's okay, take your time.
It's covering half of my screen.
Oh, I cannot help with that.
No.
Maybe try to.
How is it possible? I don't see my cursor.
You might have to click on some other program.
Click on some other program. What do you mean with that?
My Apple, I have to sometimes change windows or click on my browser to get the cursor to come back.
No, that's not what I want. Got it. Okay. Okay, so now I can start again with play.
Yeah, okay.
Okay, thank you very
Good.
much. So today we'll be talking about some geometry around some rank 3 graphs. That was the closest thing I could find with graph theory and combinatorics that I'm currently working on. And it is joint work with James Parkinson from Sydney and two of my PhD students, Magali Victor and Yannick Meijt. I will not tell the story, let's say, alphabetically, but I will make a detour, but you will see. So first, a rank 3 graph. What do we have? What must we have with a rank 3 graph? It's a rank 3 group, and that's a transitive permutation group, group G acting on set omega, and we ask that the point stabilizer of any element x of omega has precisely 3 orbits, and these 3 orbits, of course, include x itself. So if you fix x in omega, then the orbits are only x and then O1, O2. There's also a definition with orbitals, but I mean, one has to choose the definition here. So let's say these are the 3 orbits, and what you do then is for all elements y in omega, you choose arbitrarily an element of G that maps y to x. Okay, so this Gy maps y to x, and then you can make 2 graphs. The first graph, 2 in principle directed graphs. You say that y and z are adjacent. If, well, now you apply gy to z. Well, if you apply gy to y, you come back to x, right? So gy of z then belongs to either O1 or O2. Well, if it belongs to O1, then you make the graph delta 1. And if it belongs to O2, then you make the graph delta 2. And then these graphs are either opposite tournaments, so directed graphs, but opposite tournaments, or they are complementary strongly regular graphs. And that's, of course, the situation that we want. This is in particular true when O1 and O2 have different size, and most of the times they have different size, of course. So we have rank 3 graphs in this way. Let's take an example. We start with a doubly transitive group, but of course we want a rank 3 group. How do we make a rank 3 group out of a doubly transitive group? Well, we take the direct product of omega, and we let G act on both components, and then this dot 2, or that means that we can interchange the 2 components, and that's a rank 3 group called the grid case, in fact. So have here a picture, and so you have the rank 3 graph. The vertices are just the points that you see, and they are adjacent when the points are on the same vertical or horizontal line. It's a very simple rank 3 graph. But of course, what you see is that the full group of that graph is bigger. You know, it's just the symmetric group on n letters times the symmetric group on n letters, and times 2 because you can interchange them. So that's already one thing that you see here is, why can't I not go to the next slide here? Kind of stuck.
We tried to do the same thing you did before by
escape.
Uh-huh.
But the escape button doesn't work either. So no.
I think there was some written something on the slide. Maybe that's active. Pencil is active.
Yeah, I don't have a pencil, in fact, so I don't know what's happening. So you have more groups than graphs. Let's hope this doesn't repeat itself every few minutes. So you have more groups than graphs, and of course there exists classification of the rank 3 groups. In the 80s, people like Liebeck, Cantor, Liebler, Saxel, Gallagher, Fulser, they made a complete classification of all rank 3 groups after the classification of the finite simple groups was established. And from that, you can derive a classification of the rank 3 graphs. Actually, that was the initial purpose of the book I wrote with Brouwer, to write this complete classification of all these graphs in one book. But then, of course, Andries wanted to add more and more, and it became a book on strongly regular graphs. Anyway, so you can find the classification of these graphs there. Mostly when there are more groups than graphs, you can distinguish these groups in a geometrical fashion. Anyway, let me give an example here. We take the vertices, well, a second example, vertices, the pairs of 1, 2, 3, 4, 5. It's a well-known example, of course, because adjacent when they are non-disjoint, so you have the complement of the Peterson graph. And it's a Johnson graph 5, 2. The reason I take the complement is because then I have the Johnson graph. If I would have the Peterson graph, then I have the complement of the Johnson graph. But I want here the Johnson graph, in fact. So that's an example. So what is the group? The group is the symmetric group on 5 letters. And it is rank 3, because if you look at the stabilizer of the vertex 1, 2, let's say, then it has 3 orbits, 1, 2 itself. And then every pair that contains 1 or 2, and then the rest. And it's easy to see that this is rank 3, of course. So the Peterson graph is an example of a rank 3 graph. Peterson graph is an example of everything, and is also a counterexample of everything. So let's see. Okay. So what are now the main examples of rank 3 graphs? Well, the main examples, they come from classical groups. And the graphs themselves, well, then they come from the geometries that go along with these classical groups, like polar spaces, line Riemannians, also half-spin geometries, etc. So you have geometries with strongly regular point graph and a large enough collineation group. That's what we want. And so what about the exceptional groups? Well, there is only one geometry that gives rise to a strongly regular graph, and that's the E6Q geometry and the related E6Q rank 3 graph. And because these exceptional geometries, they tend to have larger diameters, these geometries. So it's only in the smallest case, let's say, of type E6 that one has a rank 3 graph. And it's a very interesting rank 3 graph. And I want to give you a combinatorial construction of that, which is not so well known. And it goes as follows. So it's a combinatorial construction, so you need combinatorial geometry. And I choose here a generalized quadrangle, GQ order 2, 4. That means that there are 3 points per line and 5 lines per point. And you see it here. So the points are two copies of the set 1, 2, 3 up to 6. I call them 1, 2, 3, 4, 5, 6, and then 1 prime, 2 prime, 3 prime, etc. And then all unordered pairs ij of that set. And so you have 6 choose 2. These are 15 elements. So 15 plus 12 is 27 points. And what are the lines? Well, the lines are the partition kind of lines. There are 15 of them, if you count well. And then you have the sets I, ij, and j prime, with I different from j, of course. And there are 30 lines like this, because for I you have 6 choices, and for j prime you have 5 choices. It's that easy. So you have 45 lines. And so you have this generalized quadrangle. And now this generalized quadrangle has a so-called spread. What is a spread? Well, a spread is nothing else than a partition of the point set in 2 lines. Somebody called this once a spread, perhaps while having breakfast or so, but it's just a partition of the point set in 2 lines. But this quadrangle has 2 isomorphism classes of spreads. So which one do I mean? Which spread do I take? It's important that I take the right spread. And well, there is a spread, it's called a Hermitian spread, but it is a spread with the following property. And it's also nice to see. So take 2 lines of that quadrangle, which are not meeting each other. We say that they are opposite or disjoint. And then for each point on each line, there is you can find a line through it that intersects the other one. So you have these 3, let's say, intersecting lines. And then that quadrangle has the property that there is a 3rd line that also meets these 3 white lines. Okay, so now this spread has the property that if the green lines belong to the spread, then also the red one belongs to the spread. So if you take as points now the elements of the spread, then you also have a kind of a geometry. And let's see what kind of geometry this is. So I have here an example, an explicit example of such a spread. It's kind of a symmetric way of writing it. And I will now interchange the order of the last column. Watch it. So I do it like this. And then if I write down these triples, if you call these 2 green lines and the red one, call this regulus, then here are in colors the elements of the lines of the same color form a regulus. So you have 3 regulus, let's say vertical ones. You have also 3 horizontal ones, and you can always check that these things are regular. But you also have these skew ones, let's say, from left top to right bottom, and also from left bottom to right top. And so you recognize the affine plane of order 3. So the spread itself is in fact an affine plane of order 3. And this is kind of a coincidence of small numbers and small geometries. Okay, but that's not so important. What we now do is we construct a 27-dimensional vector space, and we take as basis vectors EP with P a point of that generalized quadrangle. I told you there were 27 points, so each point is responsible for a basis vector. And each point is also responsible for a coordinate. So what we do is, to construct this E6 geometry, we take the intersection of 27 quadrics. And each quadric is attached to a point of that generalized quadrangle. And it has the following equation. And now I have only to tell you what is points P1, P2, etc., how these are situated somewhere in that generalized quadrangle. Well, they are points that are collinear to a fixed point x. And since I have 26 points x, I have 26 equations. And it goes as follows. So the points of one monomial, let's say xp1, xp2, the p1 and the p2 are just collinear. They are just on the line with x. p3 and p4 also on the line with x. But then, of course, there is one term that is on the right-hand side, and I have to know which one this is. And it is precisely the one that corresponds to the spread line through that point x. because the spread there is a spread line, a unique spread line to every point. The coordinates of that correspond to that spread line, you put them on the right-hand side. And so the signs are correct. And this gives you the E6Q geometry. It's a nice combinatorial construction using that generalized quadrangle. Okay, so what is the E6Q graph now? Well, these are the points that satisfy all these 27 equations. And the 2 points are adjacent when the line through these 2 points is also completely contained in all these quadrics. So that's the E6Q graph, and it's a strongly regular graph. And now, in our book, we had a look at a lot of regular sets. What is a regular set? People seem to be interested in regular sets, sometimes also called intriguing sets. And that's a set as the definition is there. So it's a subset of the set of vertices, of course. And if you take 2 points inside the set, then the number of neighbors in S of these 2 points is the numbers are the same. So a constant number of neighbors inside the set. And also if you take 2 points outside the set, then the number of neighbors that these 2 points have inside the set are also equal. So that's a regular set. And in geometry, it's sometimes called an intriguing set. Okay, there is a whole theory about these things, but the examples in the rank 3 graphs, most examples come from orbits of subgroups that have 2 orbits. If you have only 2 orbits, then of course, yeah, these conditions are satisfied because these 2 points are in the same orbit, these x and y. So these numbers must be the same. And there was one, and Andries has a program running that he could find all these subgroups. And one of these examples in the E6Q graph was a subgroup of that shape. And let me briefly explain. So you have the group triality D4Q, that's a group that acts on a generalized quadrant or a generalized hexagon, and it normalizes a cyclic group of order q squared plus q plus 1. And in fact, that q squared plus q plus 1 sounds very familiar, of course. That's the number of points of a projective plane. Well, it is a singular cycle of a projective plane inside this E6Q geometry. So there is some plane there. This group of order q squared plus q plus 1 acts as a single cycle on that. And then this triality D4Q is a normalizer of that group. Okay, so that was that gives you a regular set. And I wanted to understand more about that regular set. So I looked what it precisely did. And for that, I defined another graph. And it goes as follows. So this geometry E6Q, it has 5 spaces. There are projective spaces of dimension 5 completely contained in all these quadrics. And no more dimensions. I mean, this is the maximal dimension that is possible. So in fact, equivalently, this means that the graph E6Q has cliques of the size q to the 5th plus q to the 4th, etc. And not a single vertex more. So it has these maximal cliques. And what you can do with these cliques behave in a kind of a special behavior, because one orbit of that group of the previous page is the union of such cliques. And so we can make a graph. And you make a graph on these 5 spaces. We call them adjacent when they intersect in a plane. And that's the maximal thing in which they can intersect, in fact. That follows from some theory. It doesn't matter now. But that's the maximal dimension that they can intersect. So you can make the graph, all these 5 spaces, and adjacent when you intersect in a plane. So you have that graph inside one of these orbits. But of course, you have also that graph in the full E6Q graph. And it turns out that this is exactly the point graph of a generalized hexagon. And that's why this triality D4 is appearing there. It acts on that generalized hexagon of order Q to the third. If you don't know what generalized hexagons are, I mean, it's just a kind of a geometry. So that's an interpretation. Yeah, that's good. But then there is something else that we have to notice, and that is that each member of that group Q squared plus Q plus 1, remember, that's a single cycle, that's a kangaroo. And what is a kangaroo now? Well, a kangaroo is something that skips a distance. So you map points to distance 1 and strictly bigger than 1, but you never map a point to distance 1. The idea is that a kangaroo either stands still, so it doesn't do anything with the distance, or it jumps, right? So it never walks, let's say. So you skip the distance 1, and that's a kangaroo then. Okay, and then I was asking myself, can you go back? What if you now assume that you have an automorphism of that graph that is a kangaroo? So you map points to distance 1 and bigger than 1, but never to distance 1. So you never map a point to an adjacent one. Well, I could prove that each such kangaroo pointwise fixes the graph of that generalized hexagon, and in fact, it is inside such a group of order Q squared plus Q plus 1. And then you have that regular set associated. So this gave me the idea. So we could also do this in the original graph. We don't need to go to that other graph. So are there kangaroos in the E6Q graph is the question. So remember, a kangaroo, it maps vertices to distances 0 and 2, but never maps a vertex to an adjacent one. What can we say about such automorphisms of rank 3 graphs or strongly regular graphs, or any graph, in fact? So let me first give a baby example. So we go back to our Johnson graph, and we assume that theta is a kangaroo. So what does it mean here, a kangaroo? It means that you map pairs to itself or to disjoint ones, right? So if a point P is not fixed, then the pair P theta must be fixed. Otherwise, P theta is inside these two sets that are mapped onto each other, and that's forbidden. So P theta is fixed, and then of course, if P theta is fixed, then P is mapped to P theta and P theta back to P. So you have all these. You know precisely where P theta is going to. But if P is fixed, then for the same reason, all pairs through P must be fixed, because if a pair is not fixed, then it is mapped onto a non-disjoint pair, because P is in that pair. So you have the identity. So if some point is fixed, then you have the identity, and of course that's not a kangaroo, because you never map something to distance 2. So what have we proved? That is theta is more or less this map here, right? You can choose 1 map to 2, and then 2 back to 1, and 3 to 4, and 4 back to 3, etc. So there is only one conjugacy class of such maps, and must in fact be even, or there is no conjugacy class of such maps. So these kangaroos seem to be rare, right? I mean, there is only one example for that Johnson graph G and 2. And for the Peterson graph, there is no example, because their n is odd. So they seem to be rare. So let's take a second baby example. In fact, a more grown-up baby, because this is the Q analog of the previous example. You take lines, but I limit myself to PG5Q. So you take the graph on the lines of PG5Q adjacent when they are intersecting. That's also a rank 3 graph. And assume we have a kangaroo theta. And we do approximately the same argument. Let's assume P is not fixed. So P goes to P theta on my picture. Now, if P theta would not go to a point on that line, P theta, then you map the line P theta to an intersecting line, P theta square, but that's forbidden. So if P is not fixed, then the line P theta is fixed. Okay, so that's good. So you fix already a line. What if P is fixed? If P is fixed, then you cannot move any line through P, because if you would move the line L to L theta, it would be mapped to an adjacent line, and that's forbidden. So all lines through P are fixed. But then we have a central collineation in a projective space. It is also axial, which means you fix a lot of points, but then each fixed point is a center. That's what we just proved. And that's a contradiction. Then you have the identity. So you do not fix any point. So what you do is you have no fixed point, but every point is on a fixed line. So all these lines form a line spread. So you fix a line spread. And if you take the fixed lines and the fixed tree spaces, then they form a projective geometry, a plane, but of order q squared. In fact, it's a quadratic extension. This can also be proved in the, I didn't use finiteness here. This can also be proved in the infinite case. So you fix a projective plane of higher order, in fact. So so you can again classify this thing. So, and it looks pretty easy to do that. So there is another example, perhaps. Well, I have time to do the other example. So you have the D and Q graph, so the points of a hyperbolic quadric, and they are adjacent if they are collinear. So that's one of the standard examples of a rank 3 graph, the points of a polar space. And we take here a hyperbolic quadric, the easiest quadric that you can imagine, in fact. What you can prove here, I will not give the proof here, but what you can prove here is that the kangaroo pointwise fixes either a parabolic quadric in 1 dimension lower or an elliptic quadric in 2 dimensions lower. And that's all that you can have. That's all what the kangaroo can do. So if n is large enough, then you can, the fixed point structure of an ovoid, the fixed point structure of a collineation can never be an ovoid, because if you want to fix an ovoid, you must either fix the point or map a point to a non-collinear one, and so, but you can only do that by fixing parabolic quadrics and elliptic quadrics. So don't look for new ovoids by examining automorphisms. That's the moral here. Okay, so remember that consequence. That's why I put it in purple, because I will use it in a minute. Because now I want to return to the E6Q graph. So what does a kangaroo do there? Well, one can prove that a kangaroo there fixes exactly q to the 8 plus q to the 4 plus 1 points. And if you examine this number, then you say, yeah, okay, it could be the points of a projective plane of order q to the 4 instead of q squared, your little extension of the previous example. So that would be possible. But what you can also prove is that every pair of fixed points defines an ovoid in some D5Q subgraph. This E6Q graph has a lot of D5Q subgraphs. That's why I looked for the previous example in this D and Q graphs. So you fix an ovoid in that D5Q graph, and we saw in the last slide that it doesn't exist. You can't find such a automorphism. So it's not existent. So in the E6Q graph, you don't have a kangaroo. But what you can make out of that is the following corollary. Because this q to the 8 plus q to the 4 plus 1 points, all these points are mutually not adjacent. And it's a co-clique that satisfies the Hofmann bound. So one could rightfully call it an ovoid of the E6Q geometry. It was already noticed like this by Cooperstein some time ago. well, long time ago, in fact. And with a little bit more effort, one can show now that there is no automorphism that precisely fixes such an ovoid. Cooperstein proved that if you have an ovoid of D5Q graph, then this produces an ovoid of the E6Q graph. And but for the rest, he couldn't say anything about these ovoids in E6Q. But here we can say that don't look for them by trying to find automorphisms that precisely fix that ovoid. You won't find them because there is no automorphism that does the job. And this is a reason, I think, why it will be extremely hard to find such an ovoid in the E6Q graph, if it exists at all. And then another reason is that in the infinite case, you really fix the projective plane over quaternions or octonions. And these two cases, they do exist, but you see quaternions, they don't exist over the finite field. So that's why there are no examples in the finite case. But in the infinite case, there are examples. And if there are examples in the infinite case, then it's very hard to disprove the existence in the finite case, because everything works, so to speak. But of course, you have to find a very clever counting to disprove existence in this case. But the two arguments here, one that there is no automorphism fixing it, and the other one that it exists in the infinite case, will make it very hard, I think, to establish whether these things exist or not. Existence is hard to prove, and non-existence will also be hard to prove. So of course, there exist other kangaroo results. There are also what I call domestic kangaroos, right? I mean, what you can do is that instead of asking that you don't map vertices to distance 1, you don't map vertices to distance 2. It's not really a kangaroo, but it's a mathematical extension of the definition. You just skip one distance, or at least one distance is not allowed. And if that distance is 1, okay, then it's really a kangaroo. But if that distance is 2, then it's a domestic kangaroo, by which I mean it's domestic because you don't map points too far away. You fix it, or you map it to an adjacent one, and not to distance 2. And also there are classification results. So what you can do is you pick your favorite kangaroo and you classify it. What I did last few years is doing that in the geometries that come from the spherical buildings, or from the classical geometries. But not at all in the other rank 3 cases. I think it would be very interesting to do the same, let's say, exercise. Well, sometimes it's not an exercise, sometimes you need hard geometry to get to where you want, or even algebra. But my experience is that these kangaroos are rare, and they bring the beautiful subgeometries to the surface, like this generalized hexagon that we met there. So they bring, and they always fix large subgeometries. So in that spirit, when you examine kangaroos, you are really examining substructures and of your favorite graph, let's say. Of course, you need a graph that allows automorphisms. Otherwise, I mean, here it really goes, algebra and geometry really go hand in hand. So that's about what I had prepared when I rehearsed it. It was a bit longer, but now it's a bit shorter. I don't think that's a problem. So thank you for your attention.
Thank you very much.
Thank you. I shall try to stop the screen sharing. Yeah.
Yes. Okay, well, people are thinking, I have a question. So you had the graph constructed from E6Q, and you studied some properties of it. Did you do anything related more to E8?
Yeah, and the problem with E8, is that there is no distance regular graph associated with E8. With E7 there is a distance regular graph, but with E8 you only have the smallest geometry that you have there is the long root subgroup geometry, and this has points at distance 1, 2, and 3, but the points at distance 2 have 2 classes. So and you of course you can make a graph of it, the collinearity graph. But there's no interesting graph, let's say, where it acts on. But we also have results there for the kangaroos. Yeah.
What about E7?
E7 has a distance regular graph, a distance transitive graph of diameter 3. So that's kind of interesting. And there are kangaroos that do not map points to distance 3, so domestic kangaroos. That's fine. But you also have kangaroos that do not fix points and do not map them to distance 2. So only 1 and 3. That's kind of a shifted kangaroo. Instead of 0 and 2 is allowed, 1 and 3 is allowed, and you don't allow 0 and 2. And you can also classify these kangaroos. And then they fix large subgeometries of higher rank.
Interesting. Okay.